also mentioned in
We're
our live
already.
broadcast?
I already hit the button. Sorry, I can't end it now. But
No, it's okay. That's okay.
oh,
One of the things I want to, anyway, I want to touch upon this. And before I forget, I want to tell this. The next week, I am on travel. So there
oh
are
yeah,
two options we have. We have two
yes.
options. One of them is I can have I carry my laptop, but we are traveling from one to another place, but I may have some time in the morning. So we
Hmm.
can do a half an hour to 1 hour, or we can skip it and do it in the next week. These are the
I
two
think we can
options we
skip it
have.
because I'm also
Yeah.
traveling next week. So
Oh, okay. So that's a good idea. So we'll
yeah.
skip it. And then, so just want to let everybody know that after today's, this is the 13th, on the 20th, we are skipping. So we'll be coming back on the 27th.
Great. Okay.
So the next session will be on the 27th. I'll be sending the link at that time. So there won't be
Oh,
any
great.
link next week. Yeah.
Thanks.
Okay.
Thanks for doing all that. So, and where
Okay.
are you
Thank you.
go? So, are you going on a trip on a holiday, or is it business related? Or
Actually, I'm attending a marriage of
oh,
my nephew, which is my sister-in-law's son. We went last year. Sister-in-law's daughter got married in India. We went there. Now, sister-in-law's son is getting married in Seattle, but he's marrying somebody from Slovakia. So he fell in
oh, great.
love in Canada when he was in Canada, and then they're getting married. So we are going to that, you know, um, because
Yes.
he's like, the next level son, what we call like a nephew son type of thing. So he very, very close because, his sister-in-law,
Okay.
is my wife's sister, and, so we
Ah,
are very, very close. So I'll be going there. But before that, I'll go to Oregon where my son, he's almost graduating for the doctor. He's finished PhD, but he's going to
oh,
do a
great.
doctor and
The medical
specialist
doctor,
in
is it?
cancer specialist. Yeah. So
Oh,
we'll
all
be
right.
going there. So he's winding up in a few months. He will go some other place. So we'll be going there, and from there it's not too far. We can drive from there. So we are flying there, and then we are
Okay.
driving next. Yeah, we are driving like next Saturday
Mm,
after breakfast or whatever to Seattle. So then we'll settle in the motel there where we'll be put up for the wedding and everything.
great.
And then couple of days we'll be there 2 3 days, and then we'll
Okay.
fly back. So I'll be back by end of 23rd, 24th. I will be available. So from 17th to 24th we'll be away. I'll be away.
Yeah.
24th, 23rd night I'll be here. So 27th should not be a problem. So only that 20th won't be available.
Okay.
So
I'll just
that's
show you. So, might as well work on some stuff then. In the meantime, today.
yes, yes.
Let's see. Okay.
So
If I share, where did it go?
yeah,
That?
go ahead,
Here.
please. Thank you.
So yeah, so this was the work we did the last week. Kind of, it's a bit scrappy here. So you see, half times the mass times. So oh yeah, I did some little changes here. I just put in the x coordinate squared and then minus k divided by 2
Ah,
times the
oh,
x coordinate squared. So my thinking is to leave out the y coordinate, which is the time coordinate. Does that make sense? I think that makes sense.
yeah. To start with, yes.
Yeah,
That's good,
because
Christopher. Because
previously we had this. Remember, we would have had t. Or no, sorry, I squared, and I'm not sure if that's right. And then we would have had. So anyway, that was the idea. And there's the mass and the spring constant, um, and then you get
oh,
that. So you see the way it
okay.
starts from 0 now and goes down to
Uh-huh.
minus 1/2, which makes
Ah,
sense, right? Because the spring is, or the
yeah.
weight is going up and down from, well, I suppose the we could imagine the spring is attached maybe to plus 1/2, is it? Because it's probably not going all the way up through the,
It's an offset. Offset
yeah.
in the y-axis. Yeah.
So
because
I'm not sure.
of the potential energy, there's an offset. Okay.
Oh, okay. And then, yeah, I mean, I haven't revisited this, but these are when we start differentiating the wave. That was stuff we did previously. Now, the other thing that I looked into was I had values for something else. Now, I don't have an image. Oh, no, well, I suppose we can just graph that and graph this. So you get this kind of waveform, you know,
Ah,
that is clearly
interesting.
not a normal sine wave. So
Oh.
this just a bit of background. These basically we're graphing these numbers here,
Mm.
and these numbers come from they're part of other research I did, which may not be that useful in any sense, but basically we have the hypersphere, and then we are using like 2 by 2 matrices, either from SL2Z, or we could do SL2 or maybe, but it doesn't really matter. Even SL2Z is fine. And then we use those as rotations of the hypersphere, and then so then we can say, oh, we're at Earth, and then we rotate the hypersphere, so that means we've traveled to a different location, and then we can compare that particular SL2Z matrix with, and then use it as the basis of, let's say, a modular form. And then we can take the critical line of that modular form, which is this. Okay, so this is one of the SL2Z matrices, and this is the critical line of its modular form. So I was thinking, you know, the idea is then that we'd have, this would be the waveform of a particle at that point in the universe somewhere, you know.
Mm.
So this is what how the waveform looks over there. So then it would be, well, could we take the Lagrangian of this waveform, uh, you know, under some, maybe under gravity or something. So I tried to do that by, because this is obviously more than one sine wave mixed together. Looks like it might be a sine wave with amplitude um, 0.8, like 1/12, and then another one with, you know, an amplitude of about 3.22, and they'd have different periods. But we don't really know. So use Fourier, fast Fourier transform to unpack the two waveforms, and we get this kind of thing. So this is, presumably this is the frequency space, yeah. So there's a frequency at 73.38, and there's one at 42. Oh no, sorry, I'm reading the wrong ones. There should be a frequency at minus 31, but that doesn't sound right. We've got one at 55, we've got one at 42 and 73, and so on. And then there's also loads more down here, I think, on a smaller scale. I don't know if we can see them. They don't really register as peaks, though, so I'm a bit worried about those. And then this is the imaginary values of the critical line, and we can plot those. That gives you that kind of waveform. We can fast Fourier transform that, and you get, this is the phase space, which is interesting because it looks like to be sort of the inverse of this phase space here. Just making sure that that is right. We're doing everything correctly. Yes. Yeah, that looks right. Okay. So we continue on then. Looks like we're getting the len of the amplitude there, and then we go. So we're just plotting a range of values because we don't want to plot all of them. There's too many. And we go lin space from. So it looks like we're trying to build up the waveform here, and just recombine it. So the attempt here is to use the amplitude times the frequency, which is here, as a function of t, and then so the idea is we've taken all of this, we've we've got the frequency domain, and then we want to take the information from the frequency domain and recombine it so we get this waveform, yeah? And so that was my attempt here to do that. But as you can see, it's a failure. I don't get the correct waveform. And no matter how, you know, I have, well, hang on. Oh yeah, see, you see, so we're plotting over just a number of them for 75 to 81. So C. So we're just taking, let's say, 75. Oh, sure, that's, well, okay. So this is, let's say, that could be around here, you know, or yeah, to about here. So it's just a section of this, and then that gives us this. So, but if we were to plot the whole thing and combine all of them, you know, sum them all together, which I think we're doing here. Yeah, well, we're plus equaling them, and we're doing it for the range of the entire system, the entire frequency domain. This, yeah, we weren't plus, you see, we're not summing anything here. We're just graphing the output at each point in the frequency domain. But it still looks a bit too complicated, you know. If it's just one point in the frequency domain, we just expect one sine wave. So either I must be doing something wrong there. I don't know what it is though. And equally, I think this is incorrect as well. Oh yeah, well, I mean, it obviously is. So when we sum all of the different, so basically we're summing all of these waveforms together, we get this unholy mess here, which is nothing like the the thing we're looking for. So this has been a complete failure. But I just thought I'd share that with you so that we know.
I don't know why you multiply the amplitude with the frequency. I'm not sure. You're getting an area effect. But
you think that's a wrong thing to do? You shouldn't multiply.
I don't know what physics it gives. I have to rethink about that. Amplitude times the frequency. I don't know what it gives.
Well,
that
you know,
may be part of the problem.
But I mean, isn't that what we do? We go sine the, you know, you have amplitude times for the wave function.
Yeah, but the sine of, I mean, like Schrodinger, psi equal to psi naught, which is the amplitude, times the sine of omega t, whatever. That's the frequency that comes. So it's a sine of the frequency you have to find out, the sine or cos. So it will be amplitude times the sine of omega t. You have to do, or 2 pi nu. See, the plus and minus comes, you remember the frequency minus and plus comes because when you solve the differential equation, omega can be plus or minus, right? Square root of k or m. That's where you are.
Well, I'll try this. I don't know if this probably won't work, but oh yeah. Okay,
you multiply amplitude times the sine of the frequency times the time. You know, you multiply the frequency. Oh, you did a sine of. Oh, you did a sine. Did
Sorry,
you do
the sine of the frequency in
times the time. Frequency times the time you have to do.
Oh, you think?
Not just the frequency. Yeah, you need to do the frequency.
Frequency. Well, I've got frequency times pi there.
But no, that's not enough. 2 pi nu times time. 2 pi nu t. You have to do sine of 2 pi nu t. You have to.
Okay, well, hang on. Let me give that a go. I'll just rewrite it out down below. So the sine of the frequency times so will be times I. It should be times I, yeah, because I and t. Let's try that.
Yeah, I and t. Yeah, the t should be inside that sine. T and frequency, and the time should be inside the
sine. This is t. This is t up here, yeah. So
Yeah,
so T is a list of numbers.
time.
So I is a specific number in T. So
Oh,
so then we go for I and T. So this is time. So we just multiply that by the frequency.
yeah, times a 2 pi. Yeah,
Oh, look at that. That looks
yeah,
much
it's
better.
much better. Yeah, you're
Much
coming
better.
closer.
Coming closer, yeah, but I still don't like this.
Yeah,
This looks a bit too
they're bunched together. They're bunched together.
yeah, it looks too complicated. Let's give it a go anyway, because it's fun to
Yeah,
try these things out.
I mean,
And
you
you
get the
mentioned
right trend. Yeah,
yeah. No, it
only the
is a lot
scale is
better.
different.
Yeah, no,
The
it's
scale is different. Yeah, some scaling factor is there.
okay. So, well, what I'll do here is just I'll just take out this bit and add it in here. Now, you mentioned a couple of other things about omega, and you see,
Yeah,
I don't really have. I mean, omega being the angular velocity or
velocity.
something, but we don't really have
That
that as a term here. It's not really part of the,
no,
the
omega
equation.
is nothing but 2 pi nu, right? It's just a factor of 2 pi between
Oh,
omega and frequency. That's all. Essentially,
oh,
if you
right.
are,
Oh, yeah. Fair,
that's
fair
all it is.
point. So, how would we incorporate that? It would be, should we incorporate that?
Yeah, you should have 2 pi times the frequency times the time. That's how the sign inside uh, the sign of 2 pi nu
Oh,
t. Yeah, they should be together. If we are just talking about time aspect, then the space aspect is different.
yeah. Well, I mean, okay, but
So the
we haven't even really gotten to the Lagrangian yet. It sounds like you're talking about that, but I'm just literally I'm just literally trying to do the first step, which is graph the
yeah, this is a wave equation. Yeah, simple wave equation. This is.
so 2 pi times the time times the frequency. Is that the
Yeah,
angular? That's it.
that's the one. That's the no. That's omega t. That goes inside the sign of that. The sign, the trigonometric function, sign of that.
Yeah, we have sine of this.
Yeah.
Do I
So
need
just need
anything
a
else
two.
though? Do I now need the I don't need the sine of
Yeah,
the sine.
yeah, but normally what happens if there's a space, then it becomes kx. So kx gets added to that. But if x equal, if you're not worried about the spatial change, then we just talk about the time aspect. We just
Okay.
say psi is psi naught times sine of 2 omega or sine of omega t, which is same as psi equal to psi naught sine of 2 pi nu t. That's all. So it's a simple wave equation,
Mm,
probably simplest solution to
right.
Schrodinger equation.
And when you say new, yeah, do you mean the frequency?
Frequency, nu is the frequency.
Oh, okay. Oh yeah, that's looking interesting. Okay,
Yeah,
we still have these complicated ones as
scaling.
well though.
That's a scaling factor. If we compare that and that's stretched. The other one is just stretched of this one almost.
I don't know. I mean,
The
they're all the
earlier one,
same. They're
on
all the
top
same
one.
amplitude.
You showed the earlier one, right? On the top,
Yeah.
earlier, much earlier. The one on top, very, very much on the top. That we are trying
Oh,
to compare with. Oh, this one.
this. Yeah.
It's just a stretch. If you compress that, you get almost what we have now. Compress
I
this
don't think so.
almost.
I don't think so. These are very different. But you know what? I mean, this
Stretching.
kind of
Yeah.
thing is right. This looks
Mhm.
right. This kind of thing is right.
Oh, yeah.
This
Okay.
is not right because this obviously contains multiple sine waves mixed together. We're just trying to
Yeah.
graph the individual sine waves in the frequency domain. So,
So it's not quite Schrodinger yet. Yeah, it's not quite that sine wave. I mean, it's slightly different. So You have to figure out. I mean, but I
I
think
know,
the
yeah,
trend
this is it. I'm just kind of showing you what I'm doing, and
okay.
this is just me kind of working by myself, if you
Sure,
like.
no problem. Yeah,
I know. I mean, when I say just me working through it by my these were ideas I had, but what I can do
yeah,
is
sure.
like look up the right way to do this,
Yeah, yeah,
instead of, because I don't know. I would have assumed you just sum all of the waveforms in the frequency domain and you get back this, but apparently not. So either I'm using the wrong tool, or maybe there's something built into this package which will do it for us. Anyway,
yeah,
so that will just take a bit of research.
yeah.
That, yeah, I guess that's something I'll have to do later on. So that's that really. I'll just get out of that quickly and back to here. Okay. So yeah, that was just a bit of a background on what I've been attempting to achieve there. But I think the main thing going forward probably won't be this research. It'll be oh well, there is something that could come out of. Well, no, it won't be that aspect. That was just sort of an aside. More
Yeah.
interested in doing what we continue to do what we did last week, but
Yeah.
so we'll have the wave function like this and another one like this, and they're going to join and then become a new wave function. And the idea is how to integrate over
Mm.
those three paths, if you like, and especially over the point where it becomes discontinuous. There's a singularity in a sense. The waveforms join up
Mm.
together. So we want to figure out a way of differentiating over that point. So I have a plan in mind, but in order to get to that point, we need to go step by step. Excuse
Yeah.
me.
Sure.
So I think once we have nailed down the what is it called, the Lagrangian,
Yeah.
and we're fairly certain about what we've done there, then we can start building the waveforms in the computer, make sure they're the
Yes.
right kind, then take the Lagrangian of all those waveforms, and then hang on a sec. Yeah, and then there's further research we can do after that, but I'll obviously get some kind of results, and then we can
Yeah.
publish that. That'll be fun.
Sure.
But yeah, I think the stuff that I showed you just there probably isn't really that important. We're not going to need to, fret over it or
Actually,
anything.
you
So
maybe use it later, like a puzzle, piece of the puzzle.
yeah, it's not a it's
So
not a, it's kind of it's sort of I was attempting to bring like modular forms and elliptic curves into the Ohm research I'm doing, and I have been successful enough in doing that, particularly with the expansion rate of the universe paper. I have certain elliptic forms come up in that because there's a connection to earlier string theory research to do with the Weyl vector. But it looks like then when you plot that, I think we were discussing that before about how to plot the. Anyway, it was over email though. Remember we did some work on that. So
oh yeah,
how to get a
the
continuous.
kernel and all that. Yeah.
Yeah, no, it wasn't
Kernel
the kernel. It was to do with
because the
we have Lucas's cannonball problem with 1 squared plus 2 squared plus 3
oh yeah,
squared.
yeah, yeah.
It was
Yeah, the sigma. Yeah,
it was
the
a discrete
sigma
waveform that, and we were trying to
waveform.
take the Legendre transform of it.
Legender. Yeah.
Yeah, and then we were saying, well, we can do that by going point to point, if you like. I think was the term used.
Yeah. Yeah. Exactly. Yeah.
Yeah, and that was fine. But then but then it was the idea, well, if we could find a continuous function, then we could we could obviously
Yeah,
do
exactly. Yeah.
the real Legendre transform.
Legend.
And
Yes.
I did eventually find it, the continuous function, which is good. But what I found was it is an elliptic curve, so it goes like this, and then it goes back out here. But when it goes to that peak, there's another point here at like between -1 and -5, -0.5. I mean, -1/2 is this little bubble universe, and then you can find the critical point of that bubble universe to find like how big. So it looks like the universe had a full start, then nothing, then it exploded and came into being. So there was this like full start bubble universe that existed that ended 1/2 hour before the actual universe began. This is if you take like a literal reading of the elliptic curve graph. Now, the fullest extent of that bubble is something like has a scaling factor of around 1.26 or something like that, which is, oddly enough, very close to the value of the Higgs mass. So it looks like it goes up, Higgs mass, then it goes down to the potential, some sort of like lower thing, and then it starts again, and then the Big Bang happens, if you like. Well, not, the beginning of the universe and expansion, or scaling factor of the hypersphere. But when we go back to zero here, we can go through zero and back to the critical point of this dip before the earlier false start, and then so that's very much like the Higgs potential, isn't it? Because we have a value here which is the mass of the Higgs, and we have a dip, and then we have the actual vacuum expectation value, and then we have, so it's a weird like combination between what looks like the Higgs potential and a kind of Big Bang model. But the numbers don't fully work out though, because when you do the I have a very simplistic method of calculating the vacuum expectation from just a normal sine wave function using the mass of the Higgs. And if we use the critical point from the elliptic curve, that is 2.11324, so on. And the result of that is, well, that should be the result, in fact. And then if we plug that into, let's say, I don't know, into the mass for the W boson. I can't speak, sorry. And
the weak one, the weak theory, electroweak theory, or
yes, exactly, using the weak isospin G factor. A lot of people are saying that the G stands for muon decay, but I don't see how that is possible, because the muon decay is such a minor. I say minor.
Nucleon. Maybe a nucleon.
No, I think it's the weak isospin G factor. That makes more sense, doesn't it? Because, like you say, we're talking about electroweak theory, and the weak isospin is.
The Salam model. The Salam model. Yeah, the W
that kind of
plus
thing.
and W.
Yeah, and also weak isospin covers all of the particles. There's an isospin. Some of them might be zero, but they still have, all of the fermions have this G factor. And all of them, well, except for the ones that are zero, gain mass from the Higgs thing, not just the muon, and not just its decay rate or whatever. It's the muon decay factor. So this makes sense that it would be the weak isospin G and not some muon decay. So I just noticed there seems to be either there's a confusion online about that, or else I'm confused about it, but I don't think I am. So
I think another factor is the false vacuum versus true vacuum. I think that plays an important role, I think.
Yeah, false vacuum. Yeah, we'll get to that though.
Yeah,
but
Higgs potential may be related to the false vacuum.
Well, it is, obviously, yeah. But I mean, there's a connection there.
So the vacuum decay is actually a vacuum, false vacuum decay. So it's a vacuum decay type of situation, I think.
Well, yeah, that'd be different to the muon decay, wouldn't it? Although,
Yeah, it will be
yeah, I
different.
mean, the
Like
pulse,
I
the
have a
pulse
model.
vacuum is more about
I have a model how it
the
connects.
mass of the top
Yeah,
quark and whether it's in a
yeah,
stable or an
yeah,
unstable
yeah, yeah,
position.
yeah.
Yeah.
Yeah. It's like
Okay.
a circuit. I mean, I have the whole circuit. So it is not, it's not a simple thing. Like I said, the complexity and versus the multi-step and the order, the chemistry, that's a fundamental thing now. So the order is different. So because of that, it's not one step process, it's multi-step. So because of that, they occur differently. And that's why you have the, difference between the decay and the Higgs potential and what you are trying to do. Yeah. So I think
Well,
they are
yeah,
all
I mean,
slightly
there's a
different.
difference
They are
between
all
though,
slightly
like
different.
the muon decay, which is just the decay
Yeah,
factor.
muon decay is different. It's a
Yeah.
different.
Okay.
Yeah,
Okay.
it
Good.
will be different. It will be
Yeah. Yeah.
different.
Yeah. I think so. Okay. So when we do that anyway, we take the value for from the elliptic curve. What would be the equivalent value for the vacuum expectation of the Higgs? And then we use that as the vacuum expectation value to generate the mass of the W boson. Let's say we get 68.99 GeV, which is too low. So that doesn't work. But we can, then we can instead put the value so that we can mess around with that a bit, but it basically doesn't work. But it's still interesting. It was interesting to try it out. But another interesting part is all of these values, like the one I mentioned. What is it? It's actually 0.2113, and the other one, which is the value for the highest extent of the bubble, which would be again 0.1266, and this would work out as some value in megaparsecs. So I've forgotten what they are. I think it's like, I don't know if it's, I can look it up anyway. For the extent of the universe at that time. But all of these numbers are kind of they're highly associated with like a ton of different math problems, including flows of liquids and noise generation. And so these numbers appear in lots of different places, and they also obviously appear when you're dealing with non-monatomic tonic equations. Excuse me, I'm not saying that word right at all. It's like a bit of a tongue twister.
Functions are step functions. They are not continuous functions. They are step functions because they're multi-step process.
Non-monotonic functions.
Yeah. So it's not differentiable. Because not differentiable,
Yes,
non-monotonic, you get singularities.
That's right. Well, yeah, they have these weird critical lines. So, well, you certainly couldn't you could differentiate over parts of them. I mean, strange because they are
interval.
they
Each
are
interval,
smooth.
where it's continuous.
They are perfectly smooth and all of that, but it seems like it was not possible to use them to take the Legendre transform of you couldn't take a Legendre transform of a non-monotonic function because there was some issue that if its differential is equal to the square of its differential or something like that, or the square of the function, but
singularity.
It didn't. Even that didn't kind of. When I tested it, it seemed to pass that test, but for other reasons, it's monotonic, I think. So
yeah, you get holes there. So you take Legendre transform, you concentrate on the interval where it's continuous and do the Legendre transform for that, and then do so separately you have to do what you call separate like filters.
yeah. Well,
so that's a complexity factor.
Well, so there is definitely if I just check 27th, go back in time here to the 27th. 27. Mm. Excuse me. I've got a bit of a cough actually. Right.
I also recovering from it.
Oh yeah. Well, I don't know if I'm recovering or if it's just beginning.
Oh, now you may be getting, yeah. I mean, it's going for a long time before the new year started, and then still not completely over yet.
Oh yeah.
Like a
Well, yeah.
month,
So
month.
it's probably just a chronic cough, really.
Yeah,
So
because of the cold, the change in weather is so large here. It was very hot when it's supposed to be little cold, and then now it's very cold when it's supposed to be hot. So it's just fluctuating a lot.
oh right.
Each week is.
Yeah. I
How
mean,
about there? Your
well,
weather is kind of
why are
quirky there.
you not in your winter over there? Shouldn't it be kind of
Yeah, it's
well?
partially winter, partial winter.
Yeah, I mean, you're kind of close to the equator where you are, or not equator, but you're in a desert area, aren't you? So I wouldn't
Yeah,
imagine
yeah. Well,
wouldn't imagine
it did go down. It dipped down because
it.
from California, the storms come and they produce, depending on high pressure or low pressure, they produce, they can dump a lot of snow or water in there, or, things like that. Or they
Oh,
just become dry. When they pass through, they can become high pressure and dry. And so it creates all kinds of temperature fluctuations.
well, I've heard that the air in your state is very dry.
Yeah,
Whereas,
normally, but it can get wet because the
oh,
storms, if it passes, how it passes through is the main thing. It can pass through Arizona, which is a desert thing, or it can go up, or normally goes up to the other states, New Mexico, other places, or go up all the way up to the east, kind of try to connect there, or at the south.
okay.
So,
Well, we've a very humid climate in Ireland. It's probably more like Florida or something, I guess. I
ah,
hear
yeah,
I hear Florida is very humid.
yeah,
But
very humid in summer. Yeah,
yeah,
very humid,
how do you find
especially in
humidity?
summer.
It's just, you're from India, so originally,
Yeah,
so
we
I
have
imagine,
humidity different places. We have humidity
yeah,
like the state next to me is very highly humid. The state I
right.
am is fairly, it gets humid, but there's a sea nearby which controls. So it's fairly nice weather,
Okay.
beach weather, I would say.
Well, yeah, that's good. And I'm not sure if I'd be able to hack that, but do you see the news about those the something that happened in a mall in Miami? There was it on what was it New Year's Day or something?
Yeah.
Did you follow that?
Yeah, I follow the news. They had, yeah, they have this sudden, Texas and Florida has this sudden change in weather, the storms
Oh
that
yeah.
comes in.
No, I was talking about there was just some report about teenagers setting off fireworks or something, but then all of these
Yeah, that
people,
happens even in my state, close there. That there is a problem of teenage,
yeah,
rooms and people like that.
yeah, no, they were
That's a
beating
real
up
problem.
people with sticks and all,
It's
these,
a real problem. It's a real problem that people don't know, and that's even in the state I am, eh, near the city, the other city where originally I was.
yeah,
There's a big gang there. They formed and they created. People. It's much more than that. It's very dangerous. I mean, they have people got the teenagers got killed also and victims. Uh,
okay,
so it is a big problem, and that Florida is the other problem. So there are pockets like that. The teen violence is a pocket, and it's very unpredictable because it has created problem in other universities. Shoot out a big problem in the large problem of mass, the mass shooting, things like that.
oh
So,
yeah,
they're all somehow connected, but these gangs form, and that's where the problem is. So, it's very similar to what happens in the Middle East. It's kind of a reflection of that, probably. I don't know.
Yeah, it's hard to know. So here's the Gauss quadrature.
Yeah.
So
Quadrature.
yeah, this is excuse me.
Yeah.
These are the kind of values that I'm talking about. They see this. So I think you start with this line up here, and then you get P1 is this orange line, the diagonal, and then P2 is just like a normal quadratic curve. P3 is kind of, we're getting closer to the what do you call it, Mexican hat diagram of the which is actually P4. It's this purple one. So if this here was the mass of the Higgs, then this down here is the vacuum expectation value. But you know, it seems like you could have like this red one then could describe maybe like almost like a false vacuum state where you have like it drops down here. Or maybe actually this brown one would be better, because here you'd have the Higgs vacuum expectation value, and maybe up here the top quark. And if it was to slip past here, it would go down into a false vacuum situation of -1. So, but I'm not sure. So anyway, that's the thing, and these are where you get these values from. So it's interesting. So what I'm trying to say there is there could be a connection between the geometry of these quadratures and the elliptic curves that I was describing, which obviously seem to have some connection to the Higgs maybe, and the vacuum expectation value. Although, as we just went through there, it seems like they're not that, like I wasn't able to actually get the right answers necessarily. Like they came out slightly different. I think the most interesting one I got was something like 22 or 225 GeV, which actually is a result for the mass of the top quark, believe it or not, from the Fermi lab. They found like there was a spike in that zone when trying to measure the different values of the top quark. So that could be interesting. You know, maybe there's some connection there, but I mean, at this stage, I guess it'd be more like numerology, because it's such a difficult area to deal with, the whole thing of the Higgs potential, and the maths involved gets very complex. So I think this is it here, a hyperspace bubble. The maximum extent of the scaling factor is 0.1263928. So then if we just take 126.639 GeV would be the Higgs mass. But yeah, and this is actually a value that they thought, you know, you can look this value up, and there was originally some work done by different people, and they, using different methods, they came up with this as a potential value for the Higgs mass, you know, way back in, I think it was, well, it wasn't too long ago, it was like 2015 or something like that. But I think they've more settled on a value of around 125. So we can convert that into a volume anyway, which gives you 383 megaparsecs to the 4th power. I'm just wondering, is there any reason to go through this? So this is about the expansion rate. There's the Weyl vector with the 24. Now, actually, the Weyl vector has 26 input points. There's obviously 1 to 24, but then there's also the 0, you know, element to it, and then so these are all space-like, or not space-like, but these are the space coordinates, right? And then this is the time coordinate of the vector, if you like. I don't know if I'm saying that right, but all right. So yeah, I mean, in terms of space-like and time-like, I was looking into that briefly, and I think it's to do with the normed vectors, isn't that right? So you take the dot product to vectors, and if it's +1, it's space-like. I think if it's -1, it's time-like, and if it's 0, it's light-like. So I guess minus means it's moving along the time-like axis. 1, it's moving along the space-like axis, and then 0 is the sort of 45-degree axis where time and space are like, it's like the, I'm just guessing here, it's the light cone. Does that sound right to you, or?
Yeah, probably. I mean, I'm looking from the time domain, and I can probably work out that because I see the collapse of the time. See the algebraic time I'm talking about briefly. When you collapse, the umbrella closes. Umbrella becomes, it's
Oh
like
yeah, we'll have to look at the
one vector.
umbrella. Yeah, right. But I mean, I've apparently this vector here is a Weyl light-like vector, which means the norm of this vector should be 0. But I've so there's just the dot product. But I've calculated this, and it's not 0. So either
It's
I'm
like
calculating it wrong, or there's
Christopher
something
symbol.
I'm missing. But
Yeah, I think everything, you can think of the multi-step as different potential levels. So I think, to the wave actually is the continuous thing, continuous function, and the potential adds to that. The potential is because of the particle, right? So potential adds to that, and that's what is shifting that. So, if in terms of the radio analogy, the radio waves, you have the carrier wave, right? And the modulation. So the carrier wave is continuous. The modulation is because the particles are modulating it. So that's because of the potential energy. I think we can, and that's the Christopher symbol. I think we can connect with that. And then you have the time domain and the space domain.
well, I
So
think you should slow down there a bit, Rajan. Very
yeah, I mean,
interesting,
I'm
though.
saying that
Yeah.
eventually, I think we can connect
Yeah.
to
You need
different
to. I
potential
think
levels.
when you're formulating ideas, there you need to
Yeah,
maybe go
yeah, we will come
go
to
a
that
bit
later.
slower. I think you need to take more time. Just be
Sure.
a bit more thoughtful, because I think what you like to do is I think you're fairly inspired by this Christopher symbol thing, and that
Yeah,
makes sense. It sounds like a really good idea, but it's one thing to to say, oh, I like that guy's theory, but we also have to
yeah,
kind of
sure,
respect
sure.
that
Yeah,
that person is
we'll go through the
yeah
derivation.
that
We'll
person
go
is like
back, we'll
achieved
reset.
what they've achieved. So you kind of have to
Sure.
there might not be any way to build your own extension onto their work. Their work might be just
Yeah,
kind of a thing, and it's sort of
yeah.
self-enclosed. So there is the equation for the Lucas cannonball problem as an elliptic
Oh,
curve, and there's the elliptic curve
okay.
there.
That's the equation. That's the equation of the electric curve. Okay.
Yeah, that's the equation there, and so there's the full start of the universe, and then nothing happens,
Oh,
and then the universe begins, and it begins to scale in this way. So, but once it gets to a factor of 70, it stops. So you could draw
oh,
spheres in here, and those
yeah.
spheres would have the same size as the universe. So that's interesting. Sorry, not the size of the
Does it
universe.
support the expansion theory? Does it support the expansion theory then? Or
Well,
no?
this is to do with the anamorphic universe model. So
Yeah.
it's the expansion of the hypersphere. So
Okay.
let's say the hypersphere is here at the beginning.
Uh,
It has a certain size, like 1, and then
uh,
after 2 hours, it now has a different size. It's like grown
Yeah.
to this size. So, and then here is the tangent plane. And so the tangent plane is always infinite. So the universe was always kind of infinite. There's just nothing in the hypersphere at the beginning. And it's only when it gets to a certain size, then information is added to it, and then that gets projected onto the tangent plane. I think this is what I'm understanding. So, oh yeah, so because we have an elliptic curve here, then we can formulate that as, well, there's all the work about the non-monotonic stuff, and the critical lines are at these points. So there are the coordinate values for the maximum extent of the bubble universe, of the full start bubble. So then we can formulate this elliptic curve in terms of like around the torus to create, these kind of things where you have elliptic curve equations over a finite field P. So our finite field needs to be a prime number. So the obvious one to take is 23, because we have 0 to 23 is 24 vectors or 24 coordinates. And so then we get this kind of thing. So these yellow dots they're like the coordinate values of the modulo over this finite field, kind of, if you will. So these dots are in some ways expressive of, I'm not entirely sure what they mean, but or like how they relate back to what we're talking about. But you can take different coordinates then in the system, and you get these kind of lines, which these are kind of important for elliptic curve cryptography, but they don't have a huge. I don't really see any connection to the work I'm doing with them. I just thought it would be an interesting thing. You can also use 71 as the finite field number, because obviously if we're going up to scaling up to 70, then just one extra is also a prime number. So that could be another thing. But essentially these were null results. I didn't really get anything useful out of that. Also turning it into a modular form. Now you have these kind of Q expansions. I don't know if that's correct, if that is the actual Q, if that is the Q series for this. You have something to do with partition equations, and the number 24 appears a lot in these kind of equations. So
do they form like lattice, these
yes,
points?
yeah, they do. So these are these because this is around a torus, these wrappings of the finite field. So they can all become this is modulo the lattice, if you will. So they're so exactly right. So I think initially when they saw these kind of these coefficients, they were like, ooh, when they were looking into string theory, and obviously there's a huge amount of connection here between these lines and toruses and string theory, and then the Weyl vector and Lorentz lattices, which the Weyl vector is part of. Anyway, I think we go into that at some point. But in the end, they just realized that no, it's just describing, the symmetries of the lattice, and you start with a lattice, and then you get these symmetries. So let's say you start with the Leech lattice, and has 24 dimensions. Then you create the torus out of that and the elliptic curve, and then you connect it to the modular form, and you get 24 or multiples of, and you're like, oh, there must be some deep meaning. But apparently there isn't a deep meaning. It's just because you started with something with a symmetry of 24, and you get 24 out of it. So maybe there isn't any. This might not be an interesting area of study then, we might not. This is where you get the critical line from. That, I was thinking this could be a particle, because people have done this in the past where you go stereo project off to infinity. So you can you can actually take the Lagrangian across over of a wave function over like an infinite area, which is pretty cool. I've forgotten the guy who did that, but if I remember, I will. I don't know. I guess maybe I'll mention it another week. Oh yeah. So this is interesting. Maybe you see we have the same elliptic curve again, and we can map it over the Riemann zeta function, and it seems to make some sort of contact there. So this is a cusp in the Riemann zeta function. It's very famous, and it's around. I think it's like 1. It's centered on the value of 1, goes to infinity. So that would kind of essentially be the size of the universe. It's a bit fuzzy, but I think around here, I don't know. See, it's a bit of a confusing thing because the elliptic curve.
So the bubble grows. Does the bubble grow there?
Yeah, well, initially you have this is the bubble universe here. So you see it starts at -1, which is equal to infinity in the Riemann zeta function, because when we analytically continue the Riemann zeta function past 0, we get points like -1, which become like the sum of all the natural numbers, in Z, or no, just the natural numbers, not the counting numbers. So that's infinity. But then when we analytically continue the Riemann zeta function past 0, you get -1/12 for this. So that value was also used in string theory, or not string theory, but renormalization of infinite waves in let's say a particle well to get a finite result. So because instead of using infinity, you just say, well, infinity is equal to -1/12. So this suggests that the universe started at an infinite point, -1/12, and then grew up to a scaling factor of close to, which is the Higgs value for some reason, then stopped, then goes back down here and up here. So these cancel out sort of, and then it begins.
There's a disconnect.
Yeah,
there's kind of a disconnect.
Yeah, exactly. But from the quadrature point of view, there's no disconnect. This is like the false vacuum here, and then it goes up. There's a bit of a wiggle here down to the vacuum expectation value, and then the universe starts at 0, and then goes off, and then this is. But you see, I'm not sure if this cusp is actually at 1, because it doesn't appear to be like, we'd imagine that this is the highest value of the cusp here, but if we look, it's greater than 1, and the point at which it is greater than 1 is also the point at which the elliptic curve crosses the furthest extent of the line, which makes sense because this here would be the diameter of the hypersphere at that point. So there's some relationship here between the growth of the universe, the elliptic curve function, and the Riemann zeta function, which is interesting. I don't know if you have much knowledge of the Riemann zeta function, you might be interested in getting involved in studying this aspect of it. Now we can take we have the elliptic curve, that I was showing you here, but it's not in the Weierstrass normal form. So if we convert it into that, and we need the normal form in order to create a modular form out of it, but I don't think I did that for this paper for some reason. Maybe it's impossible. But so here's this group here of lines is the original elliptic curve, and the second group is the Weierstrass form. And we see that the Weierstrass, some of the lines of the Weierstrass form do, the most important line does cross directly through the cusp value. So there could be an issue, there could be something about that you need to convert it into the Weierstrass form as well. And then we get there could be different relationships there. I don't know.
What is that Weierstrass form? What is that Weierstrass form?
Oh yeah, it's that's a good question. So let me see if I have the answer here for you in turn visually that I can kind of, yeah, I do. So here's the original equation, and you see it's got all of these fraction terms, and then but it needs to come out exactly so that y is squared, something like that, and this is just one when you convert to Weierstrass, I think. So there's a particular form, and then if you can, so you see here, this is just one. The coefficient here is one. This is y squared, so that's good. But we've had to convert the rest of it into this. So this would be the normal Weierstrass equation for the original equation, which I just showed you.
That's some kind of a metric type of thing comes there.
Yeah, so you can have
just a coefficient.
The reason why it's called the normal Weierstrass equation is because it's only got two coefficients, if you like, in the elliptic curve. But the long Weierstrass equation then has 5. So you can only convert, you have elliptic curves of 2, or you have elliptic curves of 5.
Is that a physics associated with that?
No, this is
or just a geometry.
This is hardcore math stuff. Is there physics? Yeah, I guess there is physics stuff. Well, like I mentioned about string theory, and they tried to associate it.
Yeah.
But they had a lot of difficulty. So
yeah.
I cannot convert this into a modular form because it takes too much memory and CPU time. So even though it's quite a small equation, it's just I'm using CoCalc, and I just need to pay them more money in order to calculate this equation, and I haven't gotten around to it yet. But I guess I should at some point, but or figure out some other way to calculate it for free. That would probably be better. You can create a modular. Oh yeah, so there's the Lorentz lattice connected to all of this. It's 26 dimensional. So that's in. Yeah, so that's where I'm going with that. Well, with all of that, I like the way there could be a connection with the Riemann zeta function, and then we can scale the Riemann zeta function. I'm not sure what's going on here.
That's how you get the universe. Okay.
The real and the imaginary
2.5 hours.
Sorry, what?
That's how you calculate about the universe. 2.5 hours. You took that thing.
Well, no, the whole thing took 24 hours because there's 24.
But there's a 2.5 hour something.
There is. That is 2.5 hours could be from the beginning of the universe full start to the actual beginning of the universe. That could be 2.5 hours. I'm not sure.
Oh, okay.
Let me see. Did you read that somewhere?
I thought you had it somewhere. You had it somewhere in the recent.
This would only be an hour. I think that's a complete hour, because this is half an hour. There's a half an hour break here, and this is half an hour. So there was a full start for half an hour. There was a break for half an hour, and then the universe begins. So yeah, I think you might be mixing it up with this paper, the Marangoni cosmological catastrophe.
Could be that. It could be there. It could be there.
Because if you look, we can calculate. It's 2 hours, 10 minutes, and 13 seconds.
10 minutes. Okay.
Which is how long it would take the universe to end. You know, it will take no.
Is it Earth-based time? 2 hours means. Is it Earth-based time? 2 hours.
Yeah. The whole universe is based on Earth-based time because the whole universe is rotating. It takes 365 days roughly for the universe to rotate around the Earth. But it's not the universe that's rotating.
Connected with vacuum decay? Is it connected with vacuum decay?
There's a relationship. I'll get to that in a second, though. But I just before I do, when I say the universe is rotating, I don't mean that. I mean the hypersphere is rotating.
Yeah.
And the hypersphere is only what is it? It's only 28 megaparsecs in diameter. So there's no reason why something
there could
that
be many. You said there could be more than one hypersphere, right?
Yeah. Well, that's all like kind of philosophy at this point.
Okay.
You know, we cannot. We don't know. That's a very interesting question. It's going back to philosophical questions. I'm falling on one side of the issue because all of the data seems to be pointing that way. But you could totally formulate the entire theory on the other side, and would be very interesting to do that, I'm sure. You just won't get any of. I don't think it will just be less interesting. Well, it's not that it'll be less. Anyway, it's just harder to do and a bit more of a mind-bending thing. If you have more hyperspheres, it gets more complicated. Not to say that even in my model, there probably are multiple hyperspheres, but just keep it simple with one hypersphere rotating. That makes sense for the universe. So, we're always talking about, the universe is expanding, Well, expansion is just a translation, isn't it? It's a transformation, just as much as rotation is. So if the universe can expand, the universe can rotate. There's like the two are, if one is plausible, then so is the other. So, and especially if we're talking about it's a hypersphere that's only 28 megaparsecs in diameter, then something like that, there's absolutely no reason it couldn't rotate, especially if it's rotating in the fourth dimension where there's like infinite amount of power it's sitting in. So, what was your question again? Something to do with time.
Continue to the time you mentioned about 2 hours something.
It was the false vacuum.
Time.
There's a relationship between the Marangoni flow catastrophe and the false vacuum, but only on like a superficial level. They just happen to be. They look a bit similar. Like you can imagine, let's say this dish is the universe, or let's say this dish is the universe before this person has moved to do anything. So it's just all of these black specks are galaxies, and they're just happily sitting in the dish, which is space. Mm-hmm. Now, if the top quark moves, falls into the false vacuum area, it drags everything else with it. And then, so that's a bit like this guy dropping a droplet into the Petri dish here. It causes a Marangoni flow, which basically expands outwards at the speed of light and envelops everything in the universe, resetting the vacuum expectation value and basically destroying all matter or recreating matter in a different way, but certainly ending all life in the universe. So in that sense, it's similar, but the Marangoni flow catastrophe is formulated on completely different grounds. Like I only noticed the resemblance while I was writing the paper. Like, so there's no direct connection. One is a quantum thing and the other one is a completely own theory, if you like, or hypothesis, I should say. So what's going on here is the water is ordinary space. You can think of it as like Newtonian space with a gravitational constant of 6.67 to the 10 to the minus 11 newtons or whatever, and then kilograms per second squared or whatever. So
the universal gravitational.
Yes, the universe. Correct. Thank you. The universe gravitational constant, and that represents, or rather, I should say, the water. The surface tension of the water represents that, or the other way around, vice versa. Then we take this surfactant space substance. Now, whatever this surfactant space is, it's a different kind of space, and it has a different surface tension, which means it also has a different gravitational constant, which is slightly lower than the universal gravitational constant. So I think the word universal gravitational constant now doesn't make any sense, because we have two different gravitational constants, and those, so they stem from different universes. Essentially, we take a drop of space from one universe and drop it in our universe, and the effect is that all of the matter in the universe that wants to stay cohesive, it doesn't want to fly apart. So, on space itself, its gravitational constant forces it has cohesion, so it forces it all away from the surfactant flow, and the bubble then expands based on the Marangoni flow, which is expressed in this equation here. So you can calculate the speed of the expansion using our gravitational constant, the new surfactant gravitational constant, which is G prime, and then a number of other factors, including the Planck
viscosity and all that.
Yeah, the viscosity, and what's this one? The Planck
Mass density.
10 to the minus 19. The 0-point energy. Okay, so and that solves the cosmological constant problem then, because the equation only works with the Planck value, or the 0-point energy value. It doesn't work with the cosmological constant value. So that's the end of that.
So quantum field theory is more correct then, from that point of view.
From that point of view. That's not to say that Einstein's like wrong on like I say, mesoscopically, I think he's correct. Quantum mechanics deals with the very small, Ohm deals with the very big, and Einstein kind of sits in the middle in the galaxies, that kind of thing. Doesn't, but like extends out to Ohm in terms of gravity, and also extends to the quantum in all the ways that quantum field theory works. So Ohm doesn't deal with any of this, but basically here we have the radius expansion of the surfactant space in terms of parsecs. So up to about, I don't know, some value anyway. It's like 48 million parsecs, or so that would be 48 megaparsecs, something like that. So when it's introduced, it's obviously 0, and it quickly expands, and then the flow rate expansion slows immensely. Oh, there it is. There's the number. Approximately 45.23 megaparsecs squared is the maximum radius, which is half the circumference of the hypersphere. So it cannot expand beyond this value, because that is the maximum extent of the half of the circumference of the hypersphere. So it only gets up to a certain value, though. The Marangoni flow can only take it so far, approximately 41 megaparsecs. That's the speed. So that only takes it up to, let's say that's how far it takes it. And then, so the remaining amount, which is roughly 4.97 megaparsecs, needs to be made up by the rotation of the hypersphere. So the original hypersphere universe could have been created by a rotation, and so it's fitting that the end is also a rotation. And then because we know the size of the circumference of the hypersphere, because we know the time period that it took for the universe to form, which was 24 hours, then we can work out the rotation speed of the, we can't work out the rate, I don't think, but we can work out the speed of the remaining rotation of the hypersphere. And that gives you, that is it. The linear rotation of the hypersphere occurs at 1.88 megaparsecs squared per hour, or 523 kiloparsecs per second. So when that's this easy equation, then that works out to 2.17 hours to play out in total at a minimum. Because obviously the Marangoni flow aspect is going to happen in a flash. Like it's going to take about a second, or it's very difficult to calculate the duration of this, but it's going to be really fast. And then the remaining
It's
bit
like a
will
diffusion. Is it
yeah,
like
it's
diffusion?
yeah, it's a bit like that, like a dispersion sort of thing. So it's kind of getting into the whole thing, and then of course, see, when you were talking about strong gravity and weak gravity before, obviously that comes up along a lot in Mond, and it comes up in various strengths of gravity, which I think is what you were referring to in terms of black holes, and then out in space you have very weak gravity. But so I thought you were talking about that, and you were talking about a gradient between the two. I thought it was interesting. So I was like, oh yeah, it sounds like we're getting on a similar wavelength of this. But this would strong gravity here would just refer to the Newtonian gravitational constant, and the weak gravity really is the gravity of the surfactant space. So then the gradient between the two is what causes the mass transfer across the interface of the hypersphere surface and the bulk space, which is the four-dimensional space. And that is the Marangoni flow in essence, because we're talking about the gradient between the surface tension of the lower surfactant and the water, creating a mass transfer across the interface between the water and the air. So I think that kind of really covers that whole thing. There's our support vector machine model paper.
Yeah.
Might as well have a look at that. And I took an image from Dante's Paradiso. I think there's Dante's Inferno. And I'm not sure what Dante's in Paradiso is. I'm pretty sure because it's about this guy, the angel Virgil takes this guy on. I wonder, does he have a name in the book? Not sure, but he takes him into hell, and but he also shows him heaven at the start. So maybe there is a. So I'm not sure if Paradiso is just the start of Inferno. I'm not sure, but anyway. Now there is the equation. See, these are remember during our email correspondence about this issue to discover the transform, the space-time transform. Now you gave me the Lagrangian function, the mass of the particle. Now is that right? Should I have put in primes there instead of squared?
Yeah, it should be primes, because it's velocity, right? Half mv squared.
Yeah, okay, so I'm gonna have to change that. Is there anything else that is there any other mistakes in this? Because we're looking here
at W also you have to look at W, what the W is. That's time, right? Is it time
not connection? In this instance, because we have four
W. The W, you have to look at the W again. Let's look at.
Okay, but I mean, just in terms of a four-dimensional Lagrangian equation, that's fine. I don't have a problem with that. That looks good.
Yeah.
This is Euler-Lagrange equations. Now, I think when we were looking at we were looking at Euler equations. I think we were looking at the Lagrange. I can't remember what we looked at. Remember it here, was it?
Yeah, we were coming to that from our derivation. Yeah.
These guys. I thought we had a different name for it, but okay. But this here looks different to. Oh, where are we going? To this, doesn't it?
Yeah.
Maybe it doesn't. Let's see. So we might have to fix that.
Yeah. It's partial and full differential. So difference between the partial.
Right. Yeah.
The partial to the full differential, when you adjust the
Actually,
partial to the.
yeah, it's fairly similar. It's fairly similar. I don't know if you want to make corrections, please send them on. I think you have this paper anyway.
Yeah.
So that's it. So I put a lot of the information you gave me in the paper, and then obviously your suggestion to use the kernel equation, which formed the whole impetus for this for the rest of this research, which I think turned out pretty well.
Yeah.
Now I think you gave me some comments back, but you yeah. So other than these primes, I'll change these to primes, and I don't know if you want to make it. If you want
So
to
look
make
at
any.
the W also. Look at the W also, whether it's correct.
Oh yeah, no, I'm satisfied with the W. That's okay. Let me think here. Methodology. That's okay. And you were saying that some of this was a bit complex, overly complex, but I don't know if it is. I think anyone with background in.
Complexity, you mean? No, I'm saying complexity in a good sense.
Oh, good, good, yeah, yeah. Because I
Because
read
it covers.
yeah, I read a lot of science papers, and I can't understand what they're saying at all.
There is actually the natural thing. There is a complexity. See, I want to show this, but let me briefly mention my final analysis. Kind of like the holy grail type of thing for physics and chemistry is this order and the complexity. So the complexity I compare is like the filters, and the order I think it's like the steps, that you go through. So the steps and the filters, if you look at that, you can describe the time loop aspect also. That we'll come to
yeah.
it later. Yeah.
Well, actually, that's a good point because the time loop we didn't really mention that yet. We haven't gotten to that point, but so what we could do is actually I think there could be. I mean, there seems to be a bit of a relationship between the time loop and. Well, just basic research that I did over since the last time I spoke to you on that, so I can kind of show you sort of the conclusions I came to, and then
Okay.
and that might help your work or not. I'm not sure. So, do you want to take a quick break? Because I was sitting here with
you can take about 10 to 15 minutes.
Yeah,
10 to 15 minutes. Yeah.
Okay, you get a cup of tea or
good.
whatever. Nice one.
Yeah, we'll come back. Yeah, thanks. Yeah. Back, I don't know whether.
Okay, we're back.
So, yeah, so we were on the.
Yeah, so there was the issue. So the difference between the false vacuum expansion and the Marangoni flow catastrophe would
Uh-huh.
be if we look. So the false vacuum expansion rate happens at the speed of light. I'm not sure why it is constrained to that speed, but I suppose a lot of things are. But because we're dealing with an expansion of a surfactant space, um, it's space, you know. So like as we know in, for example, another theory that's a bit similar to Marangoni flow and false vacuum would be inflation theory, where space expanded rapidly, like far faster than the speed of light at the beginning of time. If you follow that argument.
Gerd also says same thing. Yeah.
Okay.
He
So
also.
so obviously space, you know, can move fast. So like even if we talk about the expansion rate of space under the Big Bang current standard model of cosmology, that's happening faster than the speed of light in certain areas from certain perspectives. So space, yeah, so we can have expansions of space that are faster than the speed of light, which is why the Marangoni flow catastrophe can happen so rapidly. But we also need to take into account the fact that, well, yeah, even across the hypersphere, it's happening, you know, far in excess of the speed of light. So, but there's no physical reason why that can't occur. So it's okay. Um, yeah. So then this is our support vector machine model. But I think we kind of covered all of that. I suppose there's one issue about, you know, that it, so this is how we get the radius of the hypersphere, because it looks like the, what do you call it, the decision boundary is around about the first great wall of galaxies, which is this ring of galaxies here. So that gives us the size of the universe then, which is pretty
Yeah.
handy. But it also appears that when the rotation occurs, all of the stars on the outside are going to move into the center, but all of these galaxies out around here in the interstitial sort of sphere of the hypersphere are not going to, they're not going to rotate in, they're not going to rotate out, they're just going to rotate kind of in place. And because we're putting the decision boundary possibly just outside of the first Great Wall, then and we're actually putting those on the surface of the hypersphere, then they won't rotate in either. So all of these galaxies in this, between these two lines here, will also just transform across the surface of the hypersphere. So this area out here is perfectly safe from the Marangoni flow catastrophe and the end of the universe. So that's pretty good. But if we do take, they're about 14.4 megaparsecs in distance. No, sorry, hang on. Let's go to the other.
Where is our Milky Way? Where is our Milky Way?
It is in the center.
Yeah.
Yeah.
That's what I think.
So what?
The center also is protected?
No, the center is not protected.
Right.
Yeah. So to leave to go to either one of the galaxies in the interstitial area or to the galaxies on the surface of the hypersphere, they'd all be safe places. So I think 21.6, that is the megaparsecs distance from our Milky Way galaxy at the center of this cube here to the inner circumference of the hypersphere is 21.6 megaparsecs. And then this is around 43.2 megaparsecs. So you see the interstitial galaxies are all in this area here. Our Milky Way is in the center. Probably
Andromeda.
Yeah, there might be some local group stuff in here as well. I'm not sure. It's hard to gauge the distances.
Could be part of that.
Yeah, and then so all of the Great Wall is then out here at 43.2, around the outside of the inscribed hypercube in the hypersphere. So we can work out all of the dimensions then of the hypersphere based on the radius. We get the diameter and circumference, which is actually a surface, and then the surface area, which is actually a volume, and then the volume, which is a four-dimensional unit. So that's fine, but we notice that the number 14.4 and 28.8, they are all and 43.2, they're all multiples of 12, yeah? So the number 12 seems important to me. So that's kind of why we're looking into modular forms with order 12 and 24 and things like that. But it seems to me that possibly a more, we also have time as well, because a day is 24 hours long and all of that. But so there's a lot of relationships between the number 24 and maths, physics, time as well. So since if the hypersphere rotation time is the same as Earth time, and the number 24 is part of that, it makes sense that if space and time are related, that we'd see the number 24 appear in the dimensions of space as well as time. So that makes sense. But then there's also sort of, I suppose you could look at it from religious kind of connotation. I think because we're essentially talking about the apocalypse here, the end of the universe. And is that right? Yeah, because maybe I have the wrong.
The book of Genesis tells about
yes.
about the first day, God, what happened, second day.
Yeah, exactly. So this is a retelling of the Book of Genesis here in a Syriac, I guess it would be Nestorian retelling of Genesis called the Cave of Treasures from 333 AD. But there's also another book called the Book of the Bee, which is something else, but similar kind of thing. But they, in the Book of Revelations, then, so Genesis deals with the creation, and Revelations deals with the end times, so the destruction of the universe. And but so if we look at the creation of the firmament, so this could be the outer Great Wall, could be the firmament because it's fixed in place. It's different to the stars outside, which are all antimatter in this model. Once they rotate in, they'll become matter, though, because that's how the projection works.
So the big crunch doesn't affect that. The big crunch won't affect the outer star.
Well, you could call this this is similar to a big crunch, but it's not a gravitational phenomenon. It's purely a rotational projection phenomenon.
Yeah, centrifugal and all.
There would be, I'm sure there's forces involved, but I don't know. There could be fictitious forces, because we live on the hyper tangent plane. So I mean, maybe they're fictitious forces. We don't really know. So the speed at which they come in here is not known. They could slow down to a crawl. Marangoni slows to a crawl very quickly, and then the rotation, we're just not sure about the rate. If it's going to be logarithmic or if it's going to be linear, we don't know. Logarithmic in a slowing down sense, so it starts fast, becomes slow. So in the Book of Revelations, and it says the souls of the righteous will be received on the firmament. So people who aren't going to experience the end times will go out to the safe zone, essentially. That's what the Book of Revelations is saying. And it's interesting that there will be 144,000 of those people, according to the book, which is, again, very similar
chosen
to
people.
The
chosen people.
Huh? Yes, kind of, yeah. Which is very similar to the number 144 or 14.4 megaparsecs. So I just think that's an interesting kind of connection. There's also, going back to the Marangoni flow, and seeing as how we are relating this, the universal gravitational constant to the surface tension of water, and therefore all of ordinary space is likened to water. And then if we look at the surface tension of water, not sure where it is, but basically we find very similar numbers for the surface tension of water. For example, if we have a bubble that's like a millimeter in size, the surface tension or the pressure inside that bubble is like 14.4 pascals or whatever. It's probably something like 0.00144 pascals, and then so it scales up in that kind of way. And there's also I'm not seeing it here. But I believe there was something to do with, if this is the wrong paper. What would we be looking up even? I guess water.
You have it there, right? I mean, just I thought 30. What is that? Mustard oil. You have the surface tension.
Oh yeah, so
Coconut oil.
this is another aspect of it, because in this experiment here, you can have oil sort of, if you like, dissolved into the water. So the oil generally binds with the pepper, you know, so the galaxies, which means that we now have a third type of space, because the surface tension of the oil is going to be different to the surface tension of water, which is ordinary space. So I'm saying that if there is like oil mixed in, if you like, with the water, then that would be dark matter. So dark matter is actually another kind of space called dark space, which would have a different surface tension. But here we go, I think. So this is related to the idea of the Hubble constant. So Hubble constant and scaling factor appear to be linked through the rule of 70 and 72, 69, but as they model exponential growth or expansion, and the surface tension of water, which we're using as our baseline of ordinary space, is 72. So which is also in the same range. So I guess that was it. That was basically just the observation there. There's a bigger observation to do with pressure, like I mentioned earlier, with where you can have like where the numbers come out at like 288 pascals, you know, to the -3 or whatever. I mean, I can look that up on this. I'm not exactly sure where that is. It's a Wikipedia article anyway. Maybe I could find it. Surface tension. So really, what we're talking about with surface tension then is that, you know, it's like curved space, isn't it? And
Yeah, you have
so
meniscus forming because of that, right?
yeah, so the meniscus
Meniscus.
and curved space. So it is gravity in a sense, you know. So it's very linked to Einstein's theory. Now we have Laplace
Like
pressure.
it's a
Yeah, you see,
convection.
so a bubble diameter of 1,000, what's this, micrometers, I guess, comes out
Yeah.
at Pascal 288. Then, so there seems to be like a harmonic kind of thing going on with water surface tension and pressure and the universe as a whole, which is kind of interesting. So maybe that was the word I'm looking for, harmonic. Okay, so it's not in that. It's not in that paper then. It must be in a different paper. Maybe this paper. The growth rate, the latter is harmonic. Wait, what is harmonic? The growth rate and average growth rate of the universe. I don't follow that. It's a bad sign when you don't follow your own writing.
Oh yeah, it's too many things. Yeah.
Wait a second. These are the all right. The growth rate. See, the average growth rate. Oh yeah, the average growth rate is an interesting thing. So let's look at that within the text. Growth rate. Because yeah, you can take the average growth rate, which is 228, I think, which is harmonic with the diameter. Okay. Growth rate. Let's go average. Oh, well, yeah, that's okay. Is there only one occurrence of that? Yeah, maybe I didn't mention that in the actual document then. I don't know. Average. Yeah, it's only there. Oh, for some reason I've left that out of the main content. No, I'll have to fix that as well. So that's that. I'm gonna stop sharing. Now there is back to the time loop issue, yeah. So,
yeah.
So I did a little bit of research onto that. And I was talking about Terence McKenna's work in Terence McKenna's book, The Invisible Landscape, Mind, Hallucinogens, and the I Ching. So if I look through this book, so I'll just share this then. Present. Window, yes, share that. Okay. So if I go back here, he's got the I Ching something called the King-Wen sequence of the I Ching, and no one knows why it's in this sequence. So there you can see it there. You got 17, 18. I know it's very difficult to read this. 41, 42, 43, 44, 45. So this is obviously 36, 37. Up to 64, and each of them are made from these things called trigrams, and you put them together to form.
Zoom it.
I could do my best. It's not the. I used to have this book, but I gave it away. So, but I guess it's fine to use the digital copy. There it is. There. So you see these hexagrams. They're built up as lines. So it's a bit like binary in the sense that an unbroken line, I think, is 1, and then this is 0. And you form them by throwing 3 coins down. Oh. And so whether they're heads or tails determines whether they're a broken or not line. And then you build up 6 of these, and then you look up the hexagram number, and then you use that to kind of divine the future with, you know. So you ask a question while you're throwing the coins, and then you get an answer from the book. So it's a bit like a computer program in a way, long before computers existed. It's pretty cool.
Kind of an algorithm type of thing.
Yeah, very much so. So it lends itself well to computers anyway, which is something that they found. And so what he decided to do was look at the first order differential between each of these in a sequence. So we can count here, there's this line is different, this line is different, these are the same. So we've got 2, same, same, and same. So the difference, first order differential here is 2, and then you can work out what the next one is 1, 2, 3, 4. So that's 2 and then 4, and so on. But what he found was that you will never get one with a difference of 5, yeah? Which is interesting. So there's all of the differences there. For hexagram 1, we have 6. The next one is 2, then 4, then 4, 4, 3, 2, 4, and so on and so forth. And there they are for all 64 hexagrams. The last one is 3. Now the reason why you can get first difference order for all the hexagrams and not just interstitial ones, if you like, is because it's a circle. So after you've finished with 63 and you move on to 64, you're looking at the difference between hexagram 1 and 64. So that's all good. We move on then, and then he graphs all of these 1 to 6 as just as a simple graph. Excuse me. Now, when you so there's a singularity at the beginning and the end of this. I don't know how you noticed that, but when you take this and then reverse it and overlay it on itself, you see that the start and end join up perfectly, which is kind of interesting. So he noticed this sort of singularity at the beginning and the end. And then through sort of a complicated system of maths and various things. So, so what he does is then he basically expands the waveform, makes it bigger by 64, I think, and smaller by 64. Then he overlays all of them and then takes the Fourier transform of that, which we were trying to do earlier. So this might be it would be a handy book to have from that perspective.
So you get time loops.
Right. So then when you get this this waveform, might be good to have a look at the waveform first. You eventually wind up with a waveform that looks like this.
Oh.
Yeah, so when you take the Fourier transform of this, you get this. And it goes, so what happens is you have this waveform and then there's this tiny squiggle at the end. And that squiggle there is the same as this entire waveform. It's just 64 times smaller. So we can zoom in on that and you see it there, that waveform. And this is 64 times smaller, and then you zoom in again, and then that's 64 times smaller again. So what he did was, he said, wait a second. He decided that there was an important point in history that he knew of, which was the detonation of the atomic bomb, yeah? So the purpose of this wave is to say, novelty is increasing or novelty is decreasing. But actually it doesn't matter because, like, let's say, if the bomb, if he's aligned this dip here with the bomb going off, then increasing or decreasing doesn't matter because he's saying that, the first time that people detonated a nuclear bomb was an important event, and that happened in 1945, and then from that you can work out the time wave. So he did that.
These are not abstract, are they? All abstract? Or?
How do you mean? Abstract in what sense?
The observations he got from history, from the.
Well, yeah. So you can see.
Is it empirical?
Yeah, you can kind of see here. So I think there's something going on. So basically, he's saying that each one is 64 times smaller than the previous one. Yeah. So let me think. So if iteration number 5 took 4,306 years, and that one ended in 1945, then the next one ends 67 years later. And you can do the math, and it's around, it's in the year 2012, okay?
Mine is very close. I said
yes.
1960 to 2040, and the next one is 88 years, which is 228. He's getting 212. Something like that.
Okay, so yeah, so this is it. So 67 years, and then the next one is 64 smaller again, so that's 384 days, then 6 days, then we get into minutes, seconds, the frequency or the range of low frequency sound, then low frequency radio. It's smaller and smaller, range of infrared, visible spectrum, X-ray radiation, gamma radiation, and finally the Planck's constant. Yeah. And that is the end of the.
Yeah, I believe that's more correct. The Planck time is more correct than the Planck space. So this is okay.
Oh, okay. Well, I was thinking, yeah, well, I mean, it seems like he's dealing with time. So I was thinking, why isn't he using Planck's time? But we get the idea. He's kind of talking about sizes as well. He goes from frequencies to sizes. So it's a strange bit of a change between seconds to size in terms of, but I suppose he is doing it in seconds, isn't he? 1.597.
Yeah. It's a Planck time. It's a Planck time.
Oh, very good, very good. So he got that. He's got that right. So we can also go backwards then, from 4,306 years. Multiply by 64, multiply by 64. So he's saying that the universe is actually, or there was a period of the initial period of time, which would have been, I don't know, some epoch of the universe. I forgot, he mentions what it's called. Took 72.25 billion years. And then the next
much
one,
more than 14. More than
yeah,
14
yeah.
billion. I mean, it's like,
yeah.
It's like
Exactly.
5 times, I mean, 4 times, more than 4 times, 5 times close to.
Yeah, exactly. So he's saying that is how old the universe is. It's pretty interesting. So I'm a bit confused about how he's, I mean, obviously he's anchoring the whole system on the bomb because he knows that particular date. But I've forgotten why or maybe I never knew why he's chosen it to be the 5th iteration that he anchors it on, or the 6th, depending on how you count them. So there's another guy called, let's type his name in here, because Philip K. Dick. So Philip K. Dick, yes, obviously. He wrote Do Androids Dream of Electric Sheep, which became the book, or became the movie Blade Runner. He also wrote A Scanner Darkly, which was made into a movie.
Yeah.
And he did a lot of other stuff. Okay, so he's a science fiction writer, and you can see he was born in 1928 and he died in 1982. And so the interesting thing about him and Terence McKenna is they both, I think, went to the same university, or this thing called the Occidental University. Do you know about it? Maybe it's in his early life. Yeah, I think it is. So he attended Berkeley, but there's something called Occidental, which is related to Berkeley, I think. It's been a while since I looked into this, so I'm not that familiar with what's going on. But either Terence McKenna went to Berkeley, or they both had some relationship there. But I don't think they knew each other. But they also both have, a big, like it says here, drug abuse, altered states of consciousness. So that would be similar to McKenna. Hallucinogens. He was big into the idea of mushrooms and different altered states, DMT, and that's pretty much where he got his idea from. And Philip K. Dick was also kind of interested in that, but in a different way. He was kind of also very much against it in an odd way. But he learned a lot of things through his experiences as well. And one of the things that he came up with was that there was a time loop going on, and so he was like a kind of a visionary prophet, kind of, if you will, into Gnostic Christianity. And so he believed that following Jesus's death and resurrection, the early Christians stormed some kind of temple or castle belonging to this thing called the Demiurge, which is a bit like Satan, and overthrew the castle, or this prison place. And so the Demiurge realizes he lost. So what he did was he threw time into a time loop from that moment onwards, so that time would just repeat over and over again. So and so let's say, so Jesus is born in like 180 or something, and he lives for 33 years, then he dies, then he's resurrected, and then the temple in Israel is destroyed in 70 AD, as was prophesied by Jesus. And then, so let's say there's a period of time after that, maybe 10 years, so that would be 80 years, yeah? So at the point of the near total destruction of the Demiurge's kind of empire, he throws it into a time loop. So that the time loop, I'm thinking, Philip K. Dick never states this, but would be around 70 to 80 years, like from the birth of Jesus up to the destruction of the temple, and then the time loop goes on and completes. Now, the reason why it has to be Jesus has to be involved in that, like the birthday thing, is because he had an experience where he relived some period from apostolic times where an event occurred in the Bible, and then it happened to him, but at a gas station in the, back in the 20th century. So he thought that time was on a non-self-similar loop, and that basically the events of the Bible were just repeating. The events that took place in the world at that time were just repeating over and over again. So that's interesting. So we have, let's say, 70 years for the time loop since 70 AD. I suppose you could work that out. But he says it kind of comes to an end then when the Gnostic scriptures are rediscovered in a vase somewhere in Egypt in 1943, which is very close to Terence McKenna's datum of 1945. So if we add, I think we can do it, if you just add 43 to, or if you add 70 to 43, because we're saying that his time loop is 70, then you get like 2013, which is very close to McKenna's date. But then if you use McKenna's version, which was 67 years at this point, you get to 2010. So, which is also an interesting year. A lot of people thought the world would end right around then. So, yeah. So another interesting thing is that there's 26 of these epochs, which goes back to, do we have it open? Maybe this. Kind of goes back to what we were talking about with the, the number 24 and the Lorentzian lattice. I guess you say, what is this, 25 plus 1, which is 26. So it's kind of an interesting thing there. If we look at this graph, there's 25 points on this graph, I believe. Yeah, because we have the 0 point all the way up to 24 squared, so that's 25. Then you could take the minus point of that being the time coordinate in the Weyl vector. That's what gave me the idea then to attempt to use Legendre transforms to. This is the scale factor, but obviously if we create the surface area expansion, the volumetric expansion, then we can take the Legendre transform of that to get the pressure, yeah? Which I've done, but I haven't written anything up on it really. So that would be 26 points then, if we take this minus one. So, but it's just interesting because then you could have like the first epoch, or you could go like the first epoch was 75 million years, then the next one is 112 million, or 75 billion, was it? Then 125 million. So you could go interstitially between each one. You probably get 26 up to about here, which would be the Planck thing. So I just like that similarity there, and I also like the idea of joining McKenna's work with Philip K. Dick's work and noticing that they both kind of end at the same period, but they do both end. It's like the time. If we were to look
like the Jehovah's Witness at 1996. Have you heard about Jehovah's Witness?
Oh yeah. Wasn't it 1912?
1996. 1996.
Yeah, but the original one was 1912.
Yeah, and then the next one.
Oh right, that
so
failed.
That's kind of a time loop also, kind of.
Well, I think that's less of a time loop and more of the fact that they just keep getting it wrong, so they have to push it out further.
Yeah, they adjust to the next one.
Yeah, there it is. I think this is it 1912 possibly? But I could be wrong about that. I'd have to read that. But there, yeah, it's interesting. So yeah, so but it does end though. This time loop ends, you know, like we say around 2010 to 2013. Same. I don't know when he said the loop ended, but he wasn't exactly sure when it ended. It might have ended in 1974.
According to me, it will be 2040. We are the fourth quartile of
Why do you
of
have
the
an end
current,
to your time loop? I'm just wondering.
because it starts a new time loop. So
Oh yeah, yeah,
I
yeah. Well, but this is the thing. You see, there's Philip K. Dick is saying that when the loop ends, it just ends. There's no more looping going on.
okay.
McKenna's a bit harder to pin down because he's saying that, well, you know, it's just more difficult to say with McKenna. But so that's it. So I mean, just because their loops end obviously doesn't mean that yours has to. There could be.
Yeah. I mean,
Excuse
the
me.
character changes. Each loop has a certain character. Like this loop has a very high uncertainty. Like calculate uncertainty will reduce for the next time loop. But then you have to consider the complexity and the order aspects. So, like I said, it goes through like a hill, twin peak. So we are somewhere stuck here. We have to get ourselves out. So that's a complexity factor that we'll be facing. So there is something that can happen in that. We have to climb up. It's like going against the wave, against the grain, against
Yeah.
the flow. So we have to get over that. And then what happens then is the whole question. I mean, does it create chaos, more chaos?
Mm.
Because complexity is essentially edge of chaos. It's determined by the edge of the chaos. So will there be a chaos between now and 2040, a big chaos that can totally change the whole thing in the earth and other things, is the big question. So that depends on, you know so there'll be some non-linear effect. What I mean is, when you project it, we don't see anything. That's because we are going through this yoking, whatever. But when it have very high frequency yoking, then it can throw out, like you are doing like a skiing or something up a mountain, and then you suddenly accelerate and try to get out of the mountain, snow mountain, like Alps or some other thing. Big, people go through ravines. So we are in the ravines of this mountain, of this time
Yes.
loop.
Like
So
a
we are
trough.
so we have to
Mm.
get out of this ravine of the time loop. And then
Right.
what happens then? Yeah,
Well, then you go back
that's
into
the
another
work.
ravine, don't you? You're gonna go.
Yeah, but there is a world line also. On top, there is a world line that's running. It depends on how that behaves, how this interacts. So when it comes here, it could meet the world line, and that could create a diversion. So that could throw us into a different chaotic situation. So that's uncertainty. So there's a high uncertainty now. But if we somehow magically somehow get over that, the uncertainty will decrease the next time loop, to the factor square. I think so. It will be like 0.8 now. So it will be like 0.64 the next time loop if we get
Oh,
over
okay.
this, something like that.
Well, so I thought that was interesting anyway. That there's a bit of a similarity
Yeah,
between Philip K. Dick's loop and
yeah,
your own, because well, I worked
yeah,
out it's got to be around 70 or 80 years for
yeah.
PKD's loop. So that's interesting, but obviously there's not I was thinking that wouldn't it be interesting then to reformulate McKenna's wave in terms of Philip K. Dick's wave, so that
Ah,
McKenna's wave starts like around 70 AD and then
uh-huh.
progresses and gets smaller and smaller. But obviously because it's getting exponentially smaller, that means the wave stops like really much earlier. So anyway, it didn't work. So I was thinking that it would have been interesting to do that, but it's not possible. So I would consider both McKenna's and PKD's waves to be kind of over. So, I mean, you can obviously formulate a new one if you want, different loop with different characteristics. That's kind of what I did previously with the, what was it? With that there was kind of like a rainbow wave. I think I told you about it, and it has the, it repeats every 56,000 years, which is the half-life of carbon-14. So yeah, I actually have a whole kind of web app that I created, which you know, is based on that. So it tells you like every day has a color associated with it and other things, but certainly a color and a number, I think it is. And the two are different patterns, so they only repeat after 56,000 years. But I don't have, it used to be up online, but it was taken down because I needed, the people wanted me to pay for it. So I just didn't go, and I just never renewed it and paid for it. But what I could do is just
like a web, like
yeah,
a web.
It was like an app on the web that you could just go and, you know, you'd find your birthday and find out what color you were born on, what number, what those mean, and then there was
astrology.
It's a little bit like, it's a bit like the I Ching, you know, or astrology, stuff like that. I also had another one that was based on this was it the Saros cycle of the moon or the Salas cycle? Forgotten anyway, but and you could use that. You'd put in your birthday and I think your wife's birthday, and then it would do some sort of calculation and tell you whether when was a good time to have a baby. So it's kind of like
horoscope.
Yeah. It was fun stuff. Like, but what I have all of that stuff on my computer, so I could run it on a development server and just show it to you. But it's not. I guess it's not really that.
Yeah, I was working with an astrologer, and he's original. He gets audio things, so he could calculate, and we went through some lessons, and so you know, there's a lot involved. There's a lot of statistics involved. So you know, I had lessons with many lessons, like 20 plus lessons.
You're talking about, you know, the different angles of the planets. You can have what is it? Squares and triangles.
And the main thing is uses the sun, the inclination of the sun initial, it's called something. So that's the astronomy that kind of creates. So there's a connection to astronomy and astrology there.
Yeah, for sure.
And then, so it talks about the planets, the subplanets, you know, and of course the moon. So it talks more about that.
But isn't there like
satellites, the satellites?
Ayurveda kind of astrology, or are you using kind of Western astrology here?
Hindu. No, it's Eastern. That's well versed in Indian, from India. They were really good. I mean, they were top level.
I've heard it's really good.
Yeah. They can predict. And now there's an app. You can put it in the app, India astrology, Hindu astrology, something called Ayurvedic astrology. There are different types. But if you put in there, it will give all the details, because planetary positions, how your planetary positions are linked is how everything, like your mood, when is a good time to, invest things or do some new projects, all these you can figure out.
Right. Yeah, of course. Hang on a sec. So if I go back to here. So here we have weak isospins. So these are the different fermions, and they're related weak isospins. And then I think you you have the charge Q. So to get the hypercharge is a matter of subtracting the isospin from the charge, which then gives you these kind of values. But you can multiply these by 6 to get, the weak hypercharge in a kind of a more, just in an easier to use system, if you like, of numbers. And what you find there is that you have 0 to 6 are all potential weak hypercharges, but 5 is not part of the group. So that kind of relates back to what we spoke of with the
group theory, lattice group theory.
Well, yes, it is. It's all based on that SU5 and all SU2 and SU3. But I'm thinking it kind of relates back to the first order difference of the I Ching. Remember? So so we have let's see. So there we have CC. So there are all the first order differences. There's no 5s. Obviously, we're leaving 0 out as well, but that's okay because that's in a sense a no hypercharge situation. It's where it's for like right-handed neutrinos or left-handed antineutrinos, or the ones that don't bind to the weak electroweak force. So then we can kind of use the so you could try and see if we could create the weak hypercharges from the I Ching trigrams. So that's kind of what I did here, and it's successful up to a point. You can get back the charges, but you also get weak charges, hypercharges mixed in. So it's not ideal. So it's basically saying that these aren't the same systems, and so it's not doable, but it's still interesting to think that you could reformulate the hexagrams as particles then, because I mean that's kind of what happens here. You've got it gives you a list of, you can turn the King-Wen hexagram list into a list of particles which are right-handed or left-handed, and then you can also get spins for them. So that gives you a matrix of 60 or 8x8 particles, like 64 particles. Some of them are double particles because it's hard to know which one is which.
Is it called E8? Is it like E8?
It's not like E8. It's like not related to it, but that's the reason why I'm bringing it up, is because it reminded me of your 8x8 matrix where you're multiplying.
8 by
you're multiplying by some vector.
I mean essentially the density matrix and the charge density, they form this 8x8 of all the particles. So yeah.
All right. So with this here, you see we have the electron, the down, the up, and then it goes. So the right-handed up, right-handed up, right-handed up. So you see you have 3 particles that are the same in a row, and then it appears again. Now there is a possible way to ascribe spin to all of these using the I Ching. Some of them will have superposition spins, some of them will be up, some of them will be down. And there may be other things that we can ascribe to them, certainly hypercharge, and then obviously their respective charges and such. But I don't know how useful that is to your research, but I just thought I'd share it with you, and I can send it on to you.
Yeah,
if you want to play around with it.
Yeah, we can send that.
Yeah, and I mean, I can work out the spins later and send them on to you.
Okay.
Obviously, you can find that you know their charges anyway. They're easy to find, and you can find their hypercharges.
I'm also trying to work out the logic of why the left-handed is so different from right-handed. I'm trying to find the logic, I mean, it's okay.
Yeah.
I mean, one of the things I am thinking, the large scale is that from the symmetry, what I did from the time aspect, the time matrix, is that the particle can be inside a field and the field can be inside a particle, but both are not the same. So there is an asymmetry, and the difference in the asymmetry is the mass gap. I mean, it's kind of a wild conjecture, but I think there is some something to it. I have to figure out, and that may
What is the
explain
mascot
about the left
then?
hand.
The
The
mascot
mass, but the difference is the mass. The difference is what creates the mass.
uh,
The Yeah, the
so the
difference between,
gauge, you're
see,
talking about gauge groups then.
yeah. So the main thing is that why there is a left-handed, why there is a right-handed, why there is that much difference, like top quark, bottom quark, why there is that much of a
Yeah.
difference. I'm looking from a more logical point of view,
Yeah.
how you can wrap around that. I mean, this is like a calculation. The matrix group and the symmetry group gives these answers from a standard model, but is there a underlying logic
Well, this is
that
a good
tells us?
question. Yeah, I've got something on that. So the what would you call this? Like the group theory kind of standard model
Yeah,
aspect.
the symmetry
It,
group, the
SU2,
unitary groups. Yeah,
SU2, isn't it?
SU2, SU2. Yeah,
But specifically, they're looking at SU2 for the right-handed and left-handed because you can create a
yeah,
copy of
because
SU.
up
You can
quark and
create
down quark, right? The SU2 has up quark and down quark, right? Essentially.
well, no, because like SU2, you can have. There's two copies of SU2, yeah. So
Uh-huh.
one copy is for the right-handed particles,
Oh.
and one is for the left-handed particles. And forgotten how the
Oh,
up and
I'm
the
thinking.
down. What?
I know the ket vector. The vector of this SU2 is psi of u and then psi of d, which is psi of u is the up quark, psi
Yeah.
of d is the down quark, and then
No.
they should have
Hold
2
on.
by 2 matrix associated with them. The 2 by 2 may have
Oh
the
yeah.
left-handed and right-handed, probably.
Yeah, you're right. Yeah,
Not
that's correct. Sorry, when you said up and down quark, I was thinking of spin up and spin down particles.
No, no,
That's
no.
really
Just
that's
up,
kind of confusing,
up quark
actually.
and down. No, no,
Yeah.
yeah. Psi u and d, u and d.
Yes, up and down quark. Sorry, and then also you also have like the electrons, positron, um,
Yeah.
and the neutrino. And yeah, you're right. All of these have like a 2 by 2 matrix, which means that they're all part of SU2, right? So you can have one set of SU2 that is right-handed and transforms normally, and then you have another one which is part of GL23, and they don't transform. So basically, this goes
Ah.
back to the 24 cell, where the 24 cell is self-dual. And what that means is that the copy, the 24 cell is with GL23 is there's that group is self-dual. So the double cover of the 24 cell, if you like, then that means if you multiply one matrix from the left-handed group, let's say, with the matrix on the right, you'll get a right-handed matrix. But if you multiply two right-handed matrix, you just get the identity back. You know what I mean? Or sorry, two left-handed matrices, you get the identity back, which means you just get a left-handed matrix. So it's not interacting with the other group. So therefore, the two are separate, and that's how they separate it. I'm not sure if I agree with that, because I did try out all of the matrices in SL2C and tried to multiply them, or maybe it was SL2Z, I can't remember. And I couldn't recreate the self-dual nature of the particles, and I also had a couple of other problems. But I'm assuming that their equations probably work out for the maths that they're doing, and that's all well and good. Like they have a vector, one is right-handed, one is left-handed with the psi, and then when you multiply by one of these SU2 matrices, well, it's really
it could be it could be a U1. U1 is a complex number, right? Is it because of the complex
yes,
aspect of the wave function, right?
sure. Yeah,
So
yeah,
that may be factoring into that, because you are A plus BI and A minus BI.
yeah.
So the left-handed. So is it the left-handed, right-handed? Are they associated with the rotational thing? Are they?
Well, that's a good question. Well, all I know is that, well, with the conjugacy of the, like you said, what was it, A minus BI?
Yeah, and then A plus BI times A minus BI. Yeah.
Right, but if you have like A, let's say A plus BI, then the complex conjugate of that is obviously A minus BI.
Yes.
So
yes.
so if A plus BI is, let's say, the positron, because it's positive, then its complex conjugate is its antimatter particle, the electron, because it's negative. So that's how that works.
Right-handed, left-handed. Right-handed, left-handed comes there, right?
Well, I think the right-handed, left-handed is to do with the fact of what I mentioned earlier. So let me see if I have. Oh no, it's not in this. It's in this one, I think. So we have two sets of particles in the 24 cell, but in the dual version of the 24 cell, and they come out as like these. So there's 24 of those, and then there's 24 of these. And so these are the coordinates of the 24 cell, and these are the coordinates of the dual 24 cell. But if I were to multiply this matrix by this matrix, I will get a matrix in this. So it'll transform to this. But if I multiply this by this, it will just transform back into another one of these. It won't transform into this. But if I multiply this by
non-commutative. Non-commutative.
Well, they are non-commutative because they're matrices. But if I multiply this by this, I'll get back a 20 a left-handed one. Yeah. But if I multiply it the other way around, I'll still get a left-handed one. So they are commutative in that sense. If I multiply from the other group with this group, I will also only get back a right-handed one. So that's, I think, their logic. And that actually does work. I mean, there's no problem with that. But there is a problem with there was some issue that doesn't seem to work. Oh, yeah, just the basics of trying to apply those matrices then to Clifford algebras to actually generate the left-handed and the right-handed groups. That doesn't seem to work for GL23. Also, GL23 and SL2Z or whatever, SL2Z has the potential to generate matrices with a 1 here and a 1 here, or a 1 here and a 1 here, which is not possible in GL23. So there's an issue there as well. So there seems to be, these are things that they must have solved elsewhere in some paper that they're forgotten about and they don't talk about, but I can't recreate it, so I have no idea what they're talking about. So I have a different solution to theirs, and it's very simple. I have, let's say these are all leptons, charged leptons and non-charged leptons. So are these. But you can see that this is an anti-left, and this is a right-handed matter particle. But here we have anti-right and left-handed matter particles. Yeah. So basically, we split the SL2C group into two based on the particles, based on their arrangement on the dual of the 24 cells. So we have 12 particles is in one group, and the other 12 go in the other group. And then we can split them based on the right-handed and left-handed matter and antimatter particles. And then we look at the S8 group that's associated with them, and we see instantly that the S8 group for the left-handed particles that don't interact with the weak force are like this, and the ones that do are like this. So basically, in my model, the right-handed particles are based on S8 because this is going in the direction of in the right to the right, yeah. So is this one, but this is going in the left direction, so that's a left-handed particle, yeah. So, but if we look here, there is no direction. They go, the two directions cancel each other out because this is going here and this is going there. So there is no right or left in these particles. So the weak force can't bind to these particles. And so that is the reason for the symmetry breaking. And that is a far better explanation, I think, than what they're using currently.
So it has to do with whether it can form lattice structure in a way. In a way, logic, the behind logic may be that, if you are right-handed, whether it can form a proper lattice structure or not. So,
Well, that might be a different. I'm not saying that this is the only solution, but see, my issue with what you just said there, though, is that this is a lattice structure. You see all these coordinates? They form the lattice, yeah? So...
But they are directional aspect,
No, there's no directional aspect in this. And the other problem with that is that the 24 cell is completely symmetrical, So these lattices are
but you are saying that if it goes from here to here, the pattern, that is left-handed. If it goes from here to here, it's right-handed. So it has to do with the pattern it forms.
Yeah. Well, I suppose these are those things that I was showing. These kind of things are they're permutation matrices of a kind. I think it says it there. These are the cycle notations for each one, for each of these, and there's the lepton associated with it. This is they're disjoint and directed graphs. So yeah, this would be the directed graph, if you like. This is also kind of a directed graph, but it cancels itself out. So yeah, so that's how the right-handed and the left-handed come into the picture.
Maybe it's coupling then.
Yes,
a coupling player.
I think there might be a coupling in the sense that if we look at the S8 graph for the W boson, it's a directed graph. See that? So maybe the only reason it couples with these guys because they are also directed graphs. It doesn't couple with these because there is no direction here.
Yeah.
So that's one possible solution to the problem. I mean, another way to look at it.
Makes more sense.
What?
So left-handed, the left-handed, right-handed, different coupling aspects.
Yes. Yeah. So that's pretty cool. So what do you think? Will we leave it there? How long has it been?
Yeah, we can leave it there, and then in 2 weeks we'll be there. Where are you traveling? To your hometown?
Yeah, I go back to the capital of the Republic. The Republic. I feel like I'm in Star Wars.
Where you came from, right?
Yeah. I just go to meet my family, say hi.
Right now you're in Belfast, so you go back to.
Yes. So that'll be Saturday. So you'll be able to enjoy your wedding. You won't have to.
Yeah.
You won't have to do a live stream, and I won't be able to do one anyway. It'll be next week then. Not next week, but the following week, the 27th, we'll have
the next one.
Okay.
So great. We'll have the next TEGS. Will be on the 27th.
Is there anything else you want to say before I end the stream?
No, I think we'll continue next week. I think we had because I had a few things, but we'll catch up on that. And then history of physics. I had some movie script, but but the thing is that maybe we'll start after 27th. We won't have it, but we'll decide when we should have the first episode of the history of physics.
Oh yeah,
Because
yeah. Whenever it's ready,
because I
Rajan,
had
just don't rush
yeah.
it. Just make sure it's
No, we don't rush on that because that's a very important part of eventual movie, so to say. So I'm getting some, and I'll show that probably next time if there is
great.
time. I got something about Galileo thing and how to do that. But
Very good.
it's just a draft for that. So we can start some kind of a video that forms the material towards the eventual movie. The idea is that the movie will be for scientists as well as non-scientists. People who are not. I won't call everybody is a scientist in some sense, but the thing is that people are specialized. Like we are looking at special math, special physics. The other people are not. You know, like I would know some other physics, some other math that they are using, right?
No,
So
no.
same way, other people may not know, but most people will know the fundamentals of algebra, and things like that. So more
Yeah.
people. So the movie then will not concentrate like the Oppenheimer movie will not concentrate too much on the math, but the physics aspect, how we transit, from the dark age, how the physics came into being, and why there is physics and what is the use of that, and why we became interested because it created nuclear fission, nuclear things, and also
uh,
machines like, and we use everyday life like equation of motion, like
uh,
if you want to get from here to there, we calculate the speed and then how much time is there. And then we have to have fuel. Okay, how much fuel we have. So these are all Newtonian things, right? We are indirectly using it. And the
oh yeah.
speed, when you go on highway, we are using speed. So all these are very simple things that everyday life we use. And the time clock, that's another thing that got different types of times. I also have the theory once I publish that paper, how that time points to, the algebraic time has a tensor that points to a scalar time. So that's why we are, people, there's difference. So where it points is the past or present. Like I maybe might think maybe like the mind maybe pointing to something else. Other people may be ahead of that or vice versa. So
Okay.
those are can be explained by the time matrix and the scalar aspects as well as the vector aspects. So those are the only things that will come, but also we will, make it simpler that
Uh,
a student, a school student, middle school student, or high school will be able to follow that. So
yeah, I
we'll,
think
so
well,
that's
yeah,
the whole idea.
there's like Newtonian mechanics and all, and you could probably explain that to a student,
Yeah,
of course.
and the
But
quantum mechanics,
well, you
we have
wouldn't.
to
Yeah, quantum
dilute
mechanics
it.
that'll be a bit more difficult. But then I
No,
think.
dilute it.
Hmm. Oh
The
yeah, yeah. No,
superposition,
you can do it.
we
Yeah,
can use.
true. Oh
Yeah,
yeah.
past and the present, how they their superposition, their quantum entangle, and we get
I
the
think that
present.
kind of thing though is more that's more niche. Like no, not niche. It's it's more in what you're describing there in terms of like vectors of people's mental state pointing you to the past or the
Yeah,
future. Very interesting, but more it
yeah,
seems more like metaphysical and very
yeah.
cool, like kind of like Terence McKenna's work. That's a bit more. You know what I mean? Like McKenna's work is kind of
Metaphysical, little bit
metaphysical,
more.
like yeah. So same with Philip K. Dick. So I think you're more in that kind of
Yeah, religious overtones.
yeah. When
Religious
you
over. There's some religious
actually,
overtones in there.
I mean, same with my work. Like, but you know the
Yeah,
way, like I didn't intend for any of that to come about.
yeah,
Like,
yeah.
I'm just doing the work, and then I see, oh, actually,
Connections.
the Bible spoke about this 2,000 years ago, so I have to mention it because if you don't, it's just ridiculous. So
The
it seems like
association. Yeah,
yeah. So this is why I would maybe caution the idea of like saying, oh, the dark ages set us back, because it seems like
No, not like that.
Like,
I mean, we'll dilute it.
yeah.
That's the initial script, but we'll edit that as we go along. And
just because it
we'll
seems
have
now
this much
like
script.
a lot of the work I'm doing at the moment, like, is vindicating what they were saying it back then.
Yeah.
So
No, we will.
it's like
We'll
they might
make
have
it
gotten it right.
more
So,
palatable. More acceptable. So there'll be initial draft of the movie script, right? But it will go around all of us, and then we will edit that, and then we'll come to a common area where everybody, it's okay for everybody. We don't want a neutral. It's like
I think
politically
just
neutral,
report on the events.
religiously neutral.
Don't put any spin on the history
Yeah,
in terms of
exactly.
like, oh, the Catholic Church, blah,
No,
whatever.
you don't make a judgment. We don't make judgment of things.
Yeah, just relate
We
the
are just saying
story.
history, how it happened. Just we narrate. It's like a narration of how it happened. We are not judging whether it's right or wrong.
Yeah, exactly. That's fine with me. I have no problem with that. Okay, I'll end that stream then.
Okay, have a great